Hello and welcome to this KNX RF webinar. My name is Christophe Partoens, the presenter of this webinar. So first of all, let's have a look at the agenda. So three topics actually. So first one is KNX, the overall picture. Then I will talk about KNX RF devices specifically, so the different aspects like single channel versus multiple channel, RF domains, retransmitters, communication mode, physical layer, data link layer, and the frame structure that is used for KNX RF devices during their communication. And then ETS5, and then about ETS5 and the specific, let's say, relation with RF devices. Okay, so here the overall picture. So it all started 25 years ago, more than 25 years ago already, with the KNX communication medium twisted pair, TP, so here in green. And then later on it was extended with KNX power line. And both media could be, let's say, connected together by means of a media coupler, so to be used in the same installation. Then, since some time now also, this has been again extended with RF. So that's what we see here in yellow, KNX RF devices. So that's actually how we should see them again, indeed as an extension to the already existing media types like twisted pair and power line. And also here they can be combined within the same installation by means of a media coupler. And KNX installations as such can then also be connected together via a backbone based on KNX IP. So that's the overall picture. Now, okay, let's have a look at RF devices specifically. So first of all, we can distinguish two types actually. So KNX RF ready devices, they have one single channel actually, which is one channel. So that means there's only one scan frequency. This scan frequency is set to a specific value. We call it, or represent this by F1. Right, and second type are the KNX RF multi devices. Multi indicates indeed, as expected, multiple channel devices. These devices are compatible with KNX RF ready devices. So that means whenever a multi device recognizes that a device is a ready device, it will indeed automatically change its scanning frequency to F1. So that it is indeed the same scan frequency, and that makes them of course compatible. But as such, multi-devices can also switch to other scan frequencies like F2 and F3. Those are the fast ones, and there are also two slow ones in case this would be applicable. When would that be? Well, that's what I try to explain here on this slide. So as such, a single channel device is of course, because of that fact that there's only one scan frequency, that makes these devices of course more vulnerable to interference. If exactly interference is on this scan frequency, on the F1, well, of course then communication will not be very effective here. With multi-channel devices, this problem is then solved. So in case there is indeed interference, the device has the possibility to change the scanning frequency. So that could be slow. So you switch either from S2 to S1 or vice versa, of course. And in case of fast, there are three scan frequencies to switch to. Why fast and why slow? Well, fast channels, so it depends on what kind of operation the device is used for. If it's used for operations by humans, then the device shall react quickly, so there shall be a quick response. So typically in order to operate blinds, example given. If however the application type is a slow type, let's say, so where no human actions are involved. Like a typical example would be HVAC, which as such is indeed a slow application. Well, then the slow channels are more than enough to use in this context. Because slow means that the device, of course, as such, will consume less energy, and this will of course save battery time, because most of the RF devices will be indeed equipped with a battery. Okay, RF domains, so the next aspect of an RF device. Well, an RF domain is actually a concept where RF devices are collected together within, we can say indeed, a subnetwork. There's such a subnetwork, or you can even say an RF line, but line would of course imply a cable more or less, so we rather refer to a subnetwork maybe. Okay, anyway, the maximum number of participants within such an RF domain is 255. And the RF domains are identified by the RF domain address, which is of course a specific setting within each KNX RF device. So KNX RF devices with the same RF domain address, they belong together to this specific RF domain. The RF domain address, so of which we see the abbreviation here in red, by the way, has a length of 6 octets. 2 of these octets are manufacturer specific octets, so we can say the manufacturer identifier indeed, and then 4 random octets. So in order to make sure that 2 neighbor RF domains, so to say, will not interfere with each other. That is of course the point. Okay, retransmitters and communication modes. Retransmitters are there in order to have a better communication. I said that an RF domain has a maximum of 255 devices. In practice, however, it's really hard to achieve or to reach that maximum. In order to reach that maximum, retransmitters have been defined. So that means that retransmitters can be activated within one RF domain, yes, in order to have a more effective or a better communication within that domain. However, only 3 such retransmitters can be added for one RF domain. How to do that? Well, retransmitters is actually a feature that is on board on some or most of the, so not all, on some of the KNX RF devices, and can be activated. But again, only for maximum 3 per RF domain, this can be done. 4 will simply 4 or more will simply not be accepted by the tool, by ETS. Okay, communication mode, unidirectional versus bidirectional. So also here we need to take into account older devices and of course newer devices like the energy harvesting devices, which are all by default unidirectional. Unidirectional means they can only send frames. So at runtime, these devices are indeed only able to send frames. That's the point indeed. So that is in order to save energy or battery. Of course, in the case of energy harvesting, there is no even an external energy source. So by nature, so to say, or by default, they are indeed unidirectional. However, in order to program these devices, so at configuration time, they need to be, so their bidirectional mode needs to be enabled in some way. Either we foresee an external battery or something, but for configuration, of course, the devices need to be able to receive also frames. Okay, then some specifics on the physical layer. So I just added here a few details. well, out of completeness reasons and also out of courtesy for you to easily check when you get these slides after the webinar. So we can see here indeed that FSK, so frequency shift keying, is used for the modulation. The bit coding is the Manchester bit coding. Also the chip rate, the bit rate, etc. is well mentioned on the slide. So for your information, bit rate is the speed of the actual information transfer, and this actually is not the same as the ship rate, because that's the speed of the physical signal. So just to point this out in case you were not familiar with that aspect yet. Furthermore, we have a preamble with a specific length, of course, postamble. Also interesting here is maybe to mention the Hamming distance, which is in case of KNX RF 6. That means, this 6 means that in an ideal case, up to 6 frame errors can be corrected by the receiver. So even mistakes during transmission could be corrected. Which means that as such 6 for as Hamming distance, although I'm not an expert myself, but this seems to be quite high quality. So that's what I can say. That's what I have been told. Okay, so that's the physical layer. Then the data link layer. So I can say that indeed in case of well, at runtime, the KNX RF devices will use extended group addresses in S mode. So that means that there will be a total of 8 octets used, where 2 of the octets are the, let's say, the classic or the conventional, if I can use those words, of course, KNX group address. But I think you understand what I mean. And then this will be extended with the 6 octets of the RF domain address. And again, the domain address is there to distinguish, example given, my installation from my neighbor's installation. In data link layer we will also see that devices that, so transmitters indeed, that they will insert a 3-bit LFN, so a data link layer frame number. So it's a kind of, well, it's a sequence number. So in order to prevent indeed frame duplication. That means indeed that a receiver will really check this 3-bit information, and just to make sure that 2 frames received one after another with the same, well, then the second shall be discarded. So yeah, frame duplication prevention. RF frame retransmission prevention, well, that is done by means of routing counters, and frame collision avoidance is done by means of random transmission delays. Okay, here we see the frame, so the frame structure of an KNX RF frame. So we see that it's indeed packed between, so it starts with a preamble and a postamble, and in between we see different blocks, a block 1 and then block 2, block 2, yeah, blocks of type block 2, maybe I can put it like that, and just one block of type block 1. And in between these blocks are then the CRC, the cyclical redundancy checks. And so that's the general structure. In block 1 we will find some general information about the frame, and in block 2, so the block 2 blocks, yes, contain the actual payload. So here's block 1, contains example given the signal strength and the sender's domain address example given, and in block 2 we will find the actual payload or a part of the payload, so it will contain up to 8 payload data octets. So can be anything related to payload. To useful data is also a synonym. Okay. Then the retransmitter technology, I also here want to explain it, that it is not just any well, the specifics on the retransmitter technology used, because we will use, in KNX RF, it means it's an optimized technology that is used. So here an example. Let's say that there is the situation where this source device wants to reach this destination address, and that two devices are in between, so that are used within this RF domain, are used as retransmitters, so R1 and R2. Now suppose that indeed the message 0 is the original message, so sent out by S. So it could be, there is a chance of course that the message is directly received by the destination. So that's this arrow. However, if this would fail, then there is still the receiver 1, of course, that will repeat the original message, so M0, and that will then result in M1. So that's a second chance in order to reach the destination. And there's also still, if this also fails, this M1 really also fails, then there is still the possibility that also retransmitter 2 will pick up the original message being M0 and repeats it, of course, being then resulting in M2. So there are all by all 3 chances indeed in order to reach the destination. But it is an optimized technology, because of course what could happen is that M1, so the repetition sent out by R1, is also picked up by R2 and again repeated. That could of course happen. However, the optimization is to avoid this. So that means this red arrow here, the dashed arrow, this very one, that message will never be sent. So it literally means, the optimization means, if there are 2 retransmitters, then there will only be 2 retransmissions, 2 and not more. Okay, I guess that's clear. Then ETS5 and RF devices. So in most of the cases, we will see that RF devices will be used in order to extend an existing twisted pair KNX installation. Well, in that case, as I told in the very beginning of the webinar, then in this case the so-called media couplers will be used. So twisted pair RF media couplers will be used. Such a twisted pair RF media coupler can also be used. So that's the, let's say, the runtime role of such a device. But it can also serve as a configuration or a commissioning role, because the exact same device can also be used for ETS in order to reach these devices, in order to commission these RF devices. So that's the point I wanted to make here. If, however, of course, the installation is a native RF installation, well, then of course there are only RF devices, sure. Well, in that case there is no media coupler, of course, but also here in that case there is an alternative. Then a so-called RF native USB interface should be used. And such RF native USB interfaces are offered by, if I'm not mistaken, by at least 2 of our KNX members. Okay, ETS5 supports, so I can say that ETS5 supports RF ready devices. So that's the current situation, but I can say that indeed KNX RF multi-devices as such are not yet supported, so they will be supported in the future. But even now this is not really a problem, because there's a workaround. The workaround is simply to set the KNX RF devices via the medium object property. So there's a way to do that with ETS. There's a way to change that. That's what I want to say. And then the device is indeed in in RF, so the multi-device is in RF ready mode, so to say, and will be reachable by ETS5. And then there's also the link quality aspect that I would try to address, because that's it's a specific aspect in this context. So link quality is all about communication partner transmission quality. So that is information based within each KNX RF device. So information based on which is divided over two medium object properties. One is called filter table, the other one is called quality table. The filter table is actually contains all mappings between individual addresses and entries in the quality table entry. And in the actual quality table, we will then find the quality of the transmission. So in practice, this means that, example given, information can be found about how good the link quality is with a specific device. The use case for that is, or one of the typical use cases is for ETS indeed, to know whether quick commissioning is possible or whether some patience is required. So the higher the quality, the faster ETS can commission the device. So that will have that will assure indeed an effective communication, because there's no point in trying to speed up. Otherwise, there only will be a lot of retransmissions, and that's of course not very optimal. So it is sometimes indeed just better to slow down the speed, and slowing down means that it is more effective. Because it avoids retransmissions. So that gives certainly a more optimal communication. So there are still some follow-up webinars that we can recommend, but as such the webinar is now finished. And before I conclude the webinar, I want to still present a few extra slides. And while doing that, I want to thank you for being here. I want to thank you for your attention, for considering KNX, and maybe we see one another in one of my future webinars. So thanks again, and goodbye.